So now I'd like to solve a rather classical optimization problem. Uh, you'll likely find a problem similar to this one in most introductory calculus books. Um, so the problem asks us to consider the case of an aluminum rain gutter that has 3-inch sides and a 3-inch horizontal bottom. So we're told that the sides make equal angles theta with the bottom. And the question is, what should be the measure of the angle theta in order to maximize the carrying capacity of the gutter? And so, because the volume of the gutter is going to be the product of the cross-sectional area times its length, and we assume the length of the gutter is fixed. So the only way we can increase the volume is by increasing the cross-sectional area of the gutter. And so that's essentially what our problem boils down to, is essentially maximizing the cross-section, which of course is that of a trapezoid. And so we see, of course, that because alternate interior angles are equal if two lines are parallel, then we see that this external angle to the trapezoid is going to equal this alternate interior angle theta. And similar reasoning would lead that this angle, this interior angle of the trapezoid is also theta. And so we could, if we wish, kind of partition the trapezoid into two congruent right triangles with a rectangle in the middle. And from the right triangle trigonometry, we know that because the ratio of the adjacent to the hypotenuse is the cosine of theta, that this leg of the right triangle must be 3 cos theta, and because the opposite over the hypotenuse is the sine of theta, so this leg, or the height of the trapezoid, must be 3 times the sine of theta. And so we could write down the area of the cross section. So let's first say that it simply suffices to maximize, okay, the cross sectional area of the gutter, right, to solve our problem. And so what is the area, therefore, of the cross section? Well, again, it consists of two congruent right triangles. So that would be 2 times the area of, say, this triangle, namely 1/2 the base times the height, or 1/2, say, 3 sine theta times 3 cos theta. Okay, and then of course plus the area of the middle rectangle, which is the length times the width. So that would be 3 multiplied by 3 sine theta. Okay, so this is our formula for the area of the cross section, and of course 2 times 1/2, they'll yield a product of 1. So we're left with 9 sine theta cos theta plus 9 sine theta. Okay, and of course, as it was mentioned, the angle theta here would be an acute angle, so we say where theta is positive, and well, certainly it would not, exceed, right, 90 degrees because, and we're trying to maximize the cross section. We're not going to want to turn the angle in more than 90 degrees. And so this is our area formula. We must differentiate it differentiate, right, to find the derivative of area with respect to theta. So because the first term here in the sum is actually a product, we could think of this, the derivative of the product, using the product rule. So we could take our first function, think of it as like 9 sine theta times the derivative of the cosine of theta plus the second function, cos theta, times the derivative of the first, the derivative of 9 sine theta, right? And so then to that, we must add, right, the derivative of 9 sine theta. Okay, so this would represent the formula for the derivative of the area in terms of the angle theta. So now to finish the derivative process, right, we have to differentiate the cosine of theta, so that will give us negative the sine of theta. Okay, and the derivative of 9 sine theta will be 9 cos theta. Okay, so then plus another 9 cos theta. So this is a formula for a prime of theta, but let's simplify it a little further. Right, the first product is minus 9 sine squared theta plus 9 cosine squared theta, and then plus 9 cos theta. Okay, so this is now our formula for the derivative of area. So in order to determine the critical numbers, we're going to, of course, need to figure out exactly where this derivative is equal to 0. So to do that, it may be helpful to express the derivative of area in terms of only one trigonometric function, instead of having it in terms of both the sines and the cosines of theta. And so from our basic Pythagorean identity, that the sine squared of theta plus the cosine squared of theta equals 1, we could express the sine squared of theta is always equal to 1 minus the cosine squared of theta. And so making that substitution, our formula for derivative of area now becomes minus 9 times 1 minus the cosine squared of theta plus 9 cosine squared theta plus 9 cos theta. Okay, and we can, distribute this minus 9 across the difference, and then we'll notice have a positive 9 cosine squared theta, which we could add to this other 9 cosine squared theta to end up with 18 cosine squared theta. We have a positive 9 cos theta, right? And then we have this negative 9. Okay? So here's our expanded formula then for a prime of theta, only in terms of the cosine of theta. So let's see if we could factor this at all, okay? So clearly there's a common constant factor in every term, right? Namely 9. So let's factor out the 9, so that would multiply the cosine. So that's going to multiply 2 cosine squared theta plus the cosine theta minus 1. Okay, now notice that this expression in parentheses, we could think of that as simply a quadratic expression in the variable of cosine theta. Okay, and in fact, it factors rather nicely, right, as 2 cosine theta minus 1 times the cosine of theta plus 1. So let's just double check, right, that when we multiply 2 cos theta times cos theta, right, that will yield 2 cosine squared theta. Then the mixed terms, right, the minus 1 times cos theta plus 2 cosine theta minus 1 plus 2 is plus 1 cosine theta. And of course, minus 1 times plus 1 is minus 1. So the factorization certainly works. And so this is our completely factored form for a prime of theta. So let's put that formula in a box here. Okay, and so we'll conclude that, therefore, the derivative of area, a prime of theta, will equal to 0, right, if and only if one of our two factors is 0, which would mean that either the 2 cosine theta minus 1 is 0, which requires the cos theta to be 1/2, or the cos theta plus 1 is 0, which would mean that the cosine of theta is negative 1. So let's remember, right, that theta, right, was an angle between 0 and pi over 2. And so therefore, the cosine cannot be minus 1 for any such angle. So there's no, so this part gives us no relevant solutions. And the only case, in fact, where the cosine of theta is 1/2 for theta being between 0 and pi over 2 would be if theta is exactly pi over 3, right, or 60 degrees. And so we could say that, yeah, theta equals to pi over 3 is the only, okay, relevant critical number for this problem. Right. So given that, we will take our theta interval from 0 to pi over 2. So let's say here's pi over 2, right? And we partition that interval into two subintervals based on our critical number, pi over 3. Okay, and so, right, we must examine the sign of the first derivative over each subinterval. So if our theta is between 0 and pi over 3, then we know that the cosine of theta will be greater than 1/2. So 2 cos theta will exceed 1, which is going to make this factor positive. And of course, this factor is also positive. And consequently, the product of two positives is a positive, which means that the first derivative of area is always positive for theta between 0 and pi over 3. So that means that the area function is increasing on the interval, right, from 0 up to pi over 3. So in other words, as we continue to turn in, right, the edges of the gutter up until we reach the 60-degree angle, we continuously are increasing the area of the cross section. However, once theta exceeds pi over 3, then the cosine of theta will be less than 1/2, which is going to make this first factor in the product negative. So we get a negative times a positive. So we get a negative product, or in other words, a negative derivative of area. So the area function has negative slope. The area is, in other words, decreasing on the interval from pi over 3 to pi over 2. So as we continue, beyond the 60-degree measure to raise the angle on the side of the gutter, we're going to continuously decrease the area of the cross section. And so it's clear, therefore, that the area of the gutter will be, of the cross section will be maximized and thus the volume of the gutter will be maximized when theta is pi over 3, or in other words, 60 degrees. So this optimization problem was a rather straightforward one to solve after expressing the derivative of area in terms of only one trig function, namely the cosine of theta. So I hope you enjoyed watching this. Thanks.